All right, we'll get started here. Let's see. Okay, everyone can see this? All right. Okay, so the purpose of today's, one more thing. The purpose of today's presentation was to discuss the challenges of labeling data, expert mark data, collecting that, so we can build black box and machine learning or AI algorithms to replace the experts, to automatically detect useful events in EEG or ECG, acoustic data, PPG data, accelerometer data, etc., time series data specifically. This is a bit of a storytelling exercise to describe some of the personal experiences I've had where we go down a path and invest time and money and things don't work out as we'd like. And we then rethink things and figure out that what we should have done was a bit different than we did. And then we have to spend extra time and money to do what we should have done in the first place. So my intention giving this presentation is to save you all a bit of heartache, time and money, and make your job creating algorithms that learn events in physiological data or learn how to classify patients in the medical or clinical context to make that job easier. So going forward, there's some takeaways from this presentation. One is a list of possible problems or challenges that you may encounter when you go through the data marking process and build algorithms to attempt to replace the expert or do better than the expert. I'm going to give some methods to circumvent some of these challenges that you may run into. And they can be circumvented by redefining what we're trying to do. Sometimes we try and do something and answer a problem that probably isn't the problem that we can answer, given the situation we're in. I'll also give you some ways to change how experts label the data to help you meet the performance goals that you're trying to achieve building your product and algorithm. And I'll provide some ways to solve the problem more quickly and make sure that by making sure the data that you are using to build your product and evaluate your product, make sure those data are good. So I'm also not going to pretend to have all the answers. I've encountered the problems and I can describe the problems that I did encounter and what we did. I don't have all the answers, and I'm looking to the group here to possibly provide some brainstorm or feedback. I've encountered problems some specific problems that I'll shine some light on, and some steps that can be taken to account or plan for these problems. And we'll go from there. So, as a data person, you may receive the request, or as a CEO, you may have the objective of let's take some university research that is demonstrated as medically relevant or solves a societal problem, and let's commercialize that. And that university research may use some physiological measures to, for example, provide some sort of patient diagnostic information that could be used in the real world. So let's build this, or take that from the university context and make it work in a robust way in the real world, and solve the real world problem. So you may be thinking, well, let's create a black box that is a solution, and it's going to work better than the experts. Maybe we'll tell the world that we're going to do that. One of the challenges that you may run into is that when you do get experts to evaluate the correctness of the operation of your black box or to label your data, the expert agreement among themselves might only be 80%. So going to this place of saying, we'll build a black box that's 100% correct, may not be feasible. So perhaps our goal, the problem we're solving, might be redefined as, let's create a black box that works well, as well as the majority of experts. And so maybe we get experts to label the data, which we're going to use to train and validate an algorithm. And we'll get perfect agreement, ideally, between our algorithm and the majority of experts. We also should consider what we're trying to do. We may be creating something to classify patients and classify them as healthy or not. We may be trying to create something that classifies the time series, or rather the events themselves that indicate some problem in the time series data that's acquired from the patient. And maybe we label the time series events, and we label the patient class as well. We may choose to label the patient based on some behavioral observation. So that's a fun one, because from the world of psychology, for example, if we're thinking of the context where I've been working quite a bit, the context of EEG and understanding brain function and brain health, we may be labeling patient data sets based on a 5-point scale that is derived from assessing how happy the patient seems, if they can remember things, if they can do certain cognitive tasks. And those factors themselves may lead to that 5-point scale, a 5 versus maybe a 1. And we'll want to label data that way. Also, labeling the time series events of behavior, it's important for us to know that physiological processes, like if you're measuring events in EEG or some aspect of the heartbeat waveform, that those physiological events themselves may not map one-to-one to the current best method or current label that physicians would typically use. So somewhere in there, we need to account for that mismatch or that non-one-to-one mapping. So another way of looking at this problem is maybe we want to build a useful product and a self-sustaining company that generates revenue. And therefore, we need to create something that's novel, that improves workflow in the application where it will be used, that being to reduce human labor or time. It has to address some need. Ideally, we are building something that is predictably created within some time and budget. And when we create the minimum viable product, we will have the ability to make improvements when the company is generating revenue, and we'll be able to be competitive and provide real value to the customers and solve the big problems that our hearts and minds are set on. So I've described the problem where we will use expert labeling a few different ways here. And they all have competing factors. If I define the problem succinctly and sort of raise this up a little bit to the level of educating VPs and those in the C-suite, our hope is to describe how labeling approaches, or my hope is to describe how labeling approaches have boxed me in or us into performance corners in the past, and how we can, based on what I've learned, and we can collectively come up with how we can avoid backing ourselves into a performance corner and spinning our wheels and spending time and money in the process. So I'm going to tell you a bit of story, and I'll be a little bit abstract here. And I'll say this is working in the EEG world and labeling data and creating some kind of machine learning black box classifier and putting that into a product has been an interesting experience. And there's been a lot I derive from this. So in this story, the target event, what we're trying to do is we're trying to build a black box that detects specific events in time series data. And when enough of those events are present, then we can make a decision that the patient is sick. And so we took a very simple labeling paradigm. What we did was we said, okay, well, let's have two experts vote on first of all, the patient classification, if they're sick or not, and then the presence of events in the time series data, in this case, EEG. Let's have two experts do that. And if there's a tie in any of the labels, sick or not sick, if there's disagreement in any of the labeling, sick or not sick, what if one person says sick and one expert says not sick? If there's a tie, we'll get a third expert, a tiebreaker, and we'll do a majority vote. So what we ended up with is our data that were labeled, and it wasn't consistent which expert provided which label. In some cases, we went from a pool of 3 experts potentially to 5 experts, and back and forth. So we couldn't do things like evaluate if one expert was better than the others, if inter-expert differences, we were not able to evaluate. And that was done for practical reasons, simply because experts are hard to find, and they're generally considered expensive. And so we want this assumption that saving money and time on expert labels is going to be okay, and we'll be able to reach our goal. And we also had the situation in a few different organizations I worked for where if there's only one expert, well, let's have that expert train another person, an assistant, and maybe train a pool of people. And that itself introduced some interesting challenges because that first expert would, of course, be teaching their biases and whatnot. But then also that one expert may show up in some later analysis to actually have higher agreement with the algorithm than the other experts. So what do you do there? So let's continue with the story. So let's label the time series data in this case, and we'll have experts just put marks around the event and tell us where it is, and now we know. And so we're going to build a classifier. What we do is we take those time series events and put them in one class, and take random samples of background, the non-events, and put them in another class. We train a classifier, and then evaluate the performance. And of course, we end up with some false positives. So maybe we create a third class. That third class are things that look like the target event that may indicate a patient is sick. We label those false positives as a third class or even as a second class as part of the background, and we retrain. And then we're ultimately asked to calculate some kind of performance curve, some kind of receiver operating characteristic, and maybe that comes in at like an area under the curve is 85% or something like that. And then we're asked to explain the performance or lack of. How come it's not 90? How come it's not 95? And figure that out. And this is where things get tricky because we're forced to look at what we did and figure out how we could have done things differently. And so going to that question of how do we make things better, the question is better how? Do we want to make our black box agree with the expert labels in the time series? Do we want them to somehow for this to work out that the behavioral labels, there's more agreement? Do we want to force agreement when there isn't? So this task of labeling data, experts labeling data, one way we did this was two experts, some random set of experts, would look at events in the data. Each of them would register their opinion, and if there was disagreement, we would have a tiebreaker. Okay. What about those cases where the expert's looking at the event in the data and they're not sure themselves? And so we're essentially forcing them to put a label on there. Is that helping us? And another question that has come up is when there is disagreement among experts, do we want to examine more closely why they're disagreeing? Is it because they just can't tell, or is it because there's some aspect of the feature that sort of makes them confident it isn't what the other expert thinks it is? So some options for training a classifier, again, if I put on my algorithm hat, that ask of, okay, we've got a sensitivity specificity at say 85. What can we do to improve this? So some approaches could be, well, let's try a different classifier method of generating the class boundaries. Let's try adjusting how we balance the classes. We could apply some denoising methods to the data prior to going through to the classifier. We could denoise the data prior to the experts seeing the time series events. We could go so far as creating more subclasses. We could, look at multiple classifiers or stacked or layered classifiers. All these methods would probably lead to some slight change in the sensitivity and specificity, but they're not necessarily going to be a game changer, because the reason why we are not getting our area under the curve of 95% may have nothing to do with this. And inevitably, when we're looking at how the technical ways we can improve things, someone always suggests AI and deep learning. And many of these situations in the early days when we are trying to take a concept out of the university world and get it to work in the real world, we're trying to understand what aspects of the data are essentially being used or helping to make the decision to classify one class or the other, and where points of disagreement lay between experts and the data themselves. And also often the reality is that data are collected are often non-perfect, and so we end up with a smaller set that we want to that may not be appropriate for any sort of deep learning or AI scenario. So I suggested that maybe there is an alternative way of looking at this than simply taking the technical approach and trying other classifiers or more technical methods. One might be simply to reevaluate the expert marking itself. In this case, we're not getting an area under the curve agreement with our black box and the experts of 100%. Let's ask some questions about what the expert experience is, what the expert marker experience is, and what might be happening there. So what if the experts are making more mistakes than the black box? Is it even possible to get an area under the curve? And I've alluded to this a few times, which is I can't figure this part out, how we would go about doing that. And so if there are any suggestions, please post them in the comments. And we can sort of get some discussion going at the end of this presentation. Also, going through this experience and the introspection, what's it like for if I put on my algorithm development hat, what's it like when I begin doubting the quality of the training and testing and validation data that the experts are actually marking? And this question I was able to partially answer and figure out what I could rely on in terms of the expert marking and where the gray area was or where some of my uncertainty was coming from. So these again are kind of introspective questions. If the experts make errors, how do we demonstrate the algorithm is better than them? Can we examine those cases where the expert majority vote differs? Again, it's figuring out why the experts are coming up with differences in their labels. And this is this case where maybe we see that the data are noisy, and that's one of the reasons why there are differences. And if we run the data through some sort of denoising process, maybe it's easier for them and they have more agreement. And then also repeating myself a bit, should we force experts to agree, or should we somehow be able to let them say, choose a category of like target, non-target, and unsure, or I don't know, or inconclusive? So some things to consider, having gone through this journey and trying a few things, this idea that me beginning to doubt the expert labels themselves, what I did was I trained on all the data, and then when I did test and validation, I chose to only use labels or data for which there was a unanimous labeling. All the experts agreed. And what happened was the area under the curve went from, like 85-ish% to something towards 90, 95. And so that was interesting. So I took those unsure cases, I removed them from my testing and validation. Something else I noticed is if I took the unsure cases, right, there was one expert voted one way, one expert voted the other way, and then we had a tiebreaker come in. Well, the label assigned was the majority vote. So it turns out when I took those data where there was disagreement and I compared them to the black box that was trained, we'd have an area under the curve of about 50%. So this is telling me that most of the disagreement, when I look at the whole data set, was coming from these cases where the expert labeling was not unanimous for those data. More things to consider is I started the beginning of the presentation and with the statement that experts may only agree 80% of the time. And so I did the exercise where when I was trying to figure out and trying to understand the expert labels and develop my own confidence around them, I looked at the inter-expert rate of agreement and found and calculated that it was only 80%. And then there came the idea of, okay, well, here's our ceiling. How do we do this? Because our algorithm might be disagreeing with experts because it's better than the experts. And how do we even show that? And I realized that maybe a useful metric here is, or a performance goal is, to see that the algorithm or black box we create is indistinguishable from the experts themselves in their labeling. And so we could basically calculate a rate of agreement between, say, 2 or 3 experts. And then we could add the black box as a 4th expert and see if it was possible to, if that black box stood out in any way. And one of the experiments we tried was to see which expert the black box agreed with more and whatnot. And I sort of revealed the end of the story here, which was our black box agreed with our primary expert who trained the others more often than the others. So that's the reality in the situation we were in. Yet we're held in a way to report performance for other purposes, for CE or FDA approval or whatever was promised to whoever. Again, this is going back to that question of make sure we state in a reasonable success criteria before we go about trying to do this. And again, that success criteria could be, well, let's train this as a minimum viable product so that it's indistinguishable from experts. There was a research paper when we were digging that demonstrated a way of comparing a machine learning black box algorithm to each expert separately. And so if there were 3 experts who were consistently labeling all the data sets, this becomes possible. And you can see which expert the algorithm agrees with most often, and get an ROC. You could get 3 ROCs from the expert. Now, we looked at these data, or I looked at these data many times in many different ways, and had them reevaluated by experts and so forth. So we tried a lot of things to figure out this performance, to come up with a good performance specification and to meet it. So we could consider how to improve expert agreement. And I mentioned one of the ways to do this would be to clean the data in some way, denoise it, subtract the noise floor. And a typical way I do that is using some wavelet methodologies. Another way is to incorporate some kind of data quality threshold and only evaluate data which are above that particular threshold. Only allow the experts to evaluate the data that are above that threshold, and only use those data above that threshold for training and validation. And ultimately, this incorporates the idea of a garbage detector always on the front end of anything that's using time series physiological data, is to make sure that, first of all, the data are of the type we think it is. So if it's EEG, to make sure it is, that the impedance is low and that there is actually brain activity there. So in a way, verifying that the channel through which the signal of interest is coming through is intact and clear. And the other is to make sure that when there is a signal present, that the signal is visible and can be seen above the noise floor in the data. And so ultimately, building a garbage detector that ensures these properties and essentially scores the data or just throws away data that don't meet the criteria was helpful. Another idea that came up was this idea of continuous measure of class label. Now, in the example I gave, and in the current problem described, it was essentially, is the patient sick or are they not sick? At the patient level and at the time varying signal level, is the feature, a target feature of interest that indicates sickness present or not present? And how often are they present? So could we, instead of having this sort of binary label, could we also assign some kind of confidence measure? So that when the signal, it's really evident that there is this feature in the data and the expert marker is confident that maybe they give it a score of 3. And in the case that they're really not confident, they give a score of 1. And in the case where it's not present at all, maybe they give a score of 0. And then is it possible to take these continuous measures of class label and then train the classifier to have some sort of output that lines up with that? So again, we don't end up with a binary classifier, but we end up with some sort of striation of confidence that correlates with what the experts are doing. So I haven't fully explored this idea. There were a couple other projects which briefly touched on it, but this is something that I think can move things forward, and I think that it can help build certainty around those cases where the data are quite noisy, the signal's not clear, and we can basically begin to see what would be the word here? We could begin to extrapolate what these noisy events may be. And I've also been thinking about if we were to have, say, 3 levels of classification or 4 levels of classification, we could evaluate performance characteristics for each of those levels of confidence as well. Again, it's not fully explored, but it seems like there's something there. So we also came up with this challenge of false negatives when the classifier didn't find the events in the data that are useful, and maybe we ended up with a patient classification that isn't what the patient label was. And this other question of, if we're measuring physiological data, is it possible there's something else that is interfering with, for example, the behavioral labeling? So when we're looking at a patient and making that determination they're sick, could it be something that's not physiological? And it turns out in our particular case, there's interesting psychiatric components that could be involved that ultimately make what we were building more valuable, because we were trying to measure the physiology and determine what the true state of the physiology was. Yet the labeling, because of psychiatric components, was not representative of the physiology. There's this other tricky thing, and I alluded to this previously, which is from the world of psychology or psychiatry, often there may be some kind of scale. Maybe it could be a 20-point scale that's created, and if the patient scores above 15, they're considered sick. If they score below 15, they're considered not sick. But what goes into that 20-point scale are a number of what are believed to be independent factors. And it might be the quality of sleep the patient is getting assessed, and that may be assessed in some way. It may be Maybe there's some physiological factors in there. Maybe there's some other psychological stuff and cognitive stuff in there. And this question of trying to match a measure of physiology to a 20-ish point scale that's converted to binary may be something that's simply not possible in agreement. So the idea was, could we correlate those individual factors of that 20-ish point scale to aspects of the physiology? And that's something that's an area to explore, I think, in many cases. Because as I say, some of these factors that go into the 20-point scale behavioral label are physiological and some are not. So to wrap this talk up, there are choices that have to be made early on about how a company, often a startup or a new project, how a group of people are going to label their data, have them labeled, how much emphasis they're going to put on the labeling process, how much emphasis they're going to assume, or how much they're going to assume that the data analysis and the DSP people can sort of figure it out. And the lesson has been to really think about the data labeling and planning and the experts, and sort of take prior experience and design the program in a way that we circumvent some of these challenges that we ran into. And again, that question, or the idea of defining the problem that we're trying to solve, and if I simplify it simply as, are we trying to build a classifier that's better than the experts? Like a black box that's better than the experts? Are we trying to build a black box that's similar and non-distinguishable from the experts? That's a big deal. And that communication is worthwhile because it changes a bit what we do. We can make the problem easier by doing some pilots and figuring out what is needed in terms of proving that we have good data versus not, and then creating some thresholds for what are good data and data we should just throw away because and here's another thing that I found is, if in real time we can provide feedback to the clinician or the person who's collecting the data from which we're developing the algorithms, if we can provide them feedback as to their data quality, typically we'll get a little less bad data, a little more good data, and that makes everyone's time sort of worthwhile. So that may be a first step in all of this, is a pilot to figure out data quality characteristics, to define a standard, to provide feedback, and to achieve that standard going forward. Let's see, what else do we have? We talked about the setting realizable performance goals as well. And the last point here is about ways of changing how the data are labeled to assist with reaching performance goals. Those aspects of adding a expert confidence component is really helpful. Having experts, or each expert, label all of the data, so we can then factor things out like inter-expert differences in how they report. And then there's a third one here. Well, ultimately, what was it? That was a good one. Well, we'll pick it up in the chat after the talk here, and see what we can come up with. So that's all I've got today. And let's carry this forward into the comments on the LinkedIn page. That's all for now.